Welcome back. We have been discussing now on scanning tunneling microscope. In last lecture, I have told how to fabricate the tip or probe for scanning tunneling microscope. That is an important point for STM operation, because unless and until you have a atomically sharp tip, you cannot get atomically sharp image or atomic resolution image. So, tip fabrication is an important job or important work for the operation of scanning tunneling microscope. Today, we will go to some other parts of scanning tunneling microscope, particularly the piezoelectric tube or piezoelectric scanner, and also I will introduce what is piezoelectric effect and how a piezoelectric tube works in an STM. So, this is what the main parts. We have a scanning probe and tip that we have already discussed. The second part, important part, is the piezoelectric scanner that allows the tip to scan in XYZ direction on the specimen surface. Then we have other units such as distant control or scanning unit, vibration isolation system, data processing unit. Let us first come to the piezoelectric effect. Before we go to talk about how piezoelectric tube function in a scanning tunneling microscope, first we talk about what is piezoelectric effect. This effect is nothing but transfer of electrical energy to mechanical energy or vice versa. If we apply stress or strain mechanical force to a sample, then there may be generation of the voltage, surface charge voltage, that is what piezoelectric effect. Or if we apply voltage, if there is a deformation occur or strain is generated, that is also a piezoelectric effect. So, upon applying mechanical stress to certain materials, an electric charge is generated, and that effect is called piezoelectric effect. And this was discovered by Curie brothers in 1880s, and there are many examples of piezoelectric effect where there are many examples device where piezoelectric effect works, such as speakers, electrical guitar, and the pocket lighter, where these piezoelectric materials are used. We have two type of piezoelectric effect. That means the piezoelectric effect can be classified into two types, direct or indirect. Direct piezoelectric effect is when we apply the force or strain, to the material, and an electric charge is developed, and that is what is called direct piezoelectric effect. And direct piezoelectric effect is example is like we have this lighter, pocket lighter, which is once we put mechanical force, a voltage is generated, and that is used to that voltage which generates is that produce the lightning spark. And also other application include like sensor technology, touch screen. When we touch, we put a force, and that generates the voltage, and that is what the sensor technology. Those are direct piezoelectric effect. And indirect or inverse or converse piezoelectric effect is the effect when we apply a variable voltage, and then deformation occurs to the crystal. That means dimension of the material changes. That is what the inverse or indirect piezoelectric effect. Examples like we have a natural quartz, which is a crystalline material that saw piezoelectric effect. We have also engineering material such as lead zirconate titanate, or in the short form it is called as PZT. That is a very good piezoelectric material. Here this engineering material is this PZT is poled to impact the piezoelectric effect. That means, I will say what is pole and how polling is done. Polling is done to impact the piezoelectric effect to engineering materials such as lead zirconate titanate, and it has a quite high sensitivity. It has a quite high sensitivity and also a high Curie temperature. That is why more extensively used in many applications. Just having a little piezoelectric effect may not be enough. If the effect is strong enough, then only it can be used for practical use. In that sense, PJT have quite good or strong effect to be that is used in many practical applications. Out of 32 crystal classes, 22 such crystal classes have material showing piezoelectric effect, and this piezoelectric effect is associated with the crystal with non-centrosymmetric crystals, where there is no inversion center, and those only will show piezoelectric effect. And let us see some that means this PJT example, how in the microscopic level a PJT saw the piezoelectric effect. So, in the left side what you see is here a unit cell. In the one you see a unit cell where we have a divalent lead atom at the corner of the unit cell. There is a blue color is seen. Then oxygen at the face centered position, that is in the outer face of the unit cell. Then forming a octahedrons, this red color oxygen, and then we have a tetravalent tetravalent titanium, a little green color, which is displaced from the center of the unit cell, displaced upward in the center of the unit cell. This is a unit cell of PJT in the 1, and in the 2 I saw a side view of PJT, where we can see that titanium, tetravalent titanium is displaced upwards from the center, and this arrow indicates direction and size of the dipole moment. As I was saying that these piezoelectric effects is seen in a crystal which is non-centrosymmetric. What means by non-centrosymmetric is that the crystals which do not have a inversion center, and therefore it should have it should produce a net electric dipole moment. If it has a inversion center, like if a dipole is formed in the position let us say x, and there will be, if there is an inversion center, there will be opposite dipole at position minus x, and they will cancel each other, therefore, there will be no net dipole moment. And in that cases that type of crystal cannot show piezoelectric effect. For piezoelectric effect to occur, it should be non-centrosymmetric, therefore, there should be a dipole moment inside the crystal. And in the second, what you see here, this is a arrow which showing the direction and size of the permanent electric dipole moment. This is showing permanent electric dipole moment in the z direction, and here PJT is poled in the polling was done with in the z direction. So, because of this dipole moment, there will be net charge at the xy planes of this crystal, like a capacitor with a dielectric material inside. The direction along which permanent dipole moment here is taken in the z direction in the 2, and here material is said to be poled along the z direction. I will come to tell you what is pole and what is polling. This is 2. In the third, what we see, if we compress along the z axis, if we compress along the we compress the unit cell along the z axis, the dipole is reduced. the magnitude of the dipole is reduced. As the magnitude of the dipole is reduced, the direction is remains same, but the magnitude is reduced. Therefore, the charge will reduce and therefore, the charge will reduce and the dipole the electric dipole moments also will decrease, and that lead to that would reduce the charge and dipole moment because of the strain along the z direction, that is what compression is done, which is the Pauling direction. As I told, z direction was the Pauling direction. When strain is applied along the same direction of Pauling, this was Pauling in z direction, Pauling was done, then it is called longitudinal piezoelectric effect. Here compression is done in the z axis, and that is the same axis along which the Pauling was done. That is why it is called longitudinal piezoelectric effect, and that process also will have the surface charges which will be reduced compared to here in the 2, but still we have a electric dipole moment. But in the fourth cases here, in the fourth cases, a strain is applied along the x direction, strain is applied along the x direction. As strain is applied along the x direction, but in the x direction there will be no dipole moment change. There will be no dipole moment change because in the x direction is not centrosymmetric. So, the requirement is that requirement of the piezoelectric material is that it should be not centrosymmetric, but in the x direction it is centrosymmetric. Therefore, even though we put a strain in the x direction, it will not produce dipole moment change, no change in the dipole moment along the x direction, but the applying a strain along the x direction would also change the, it will also produce some strain in the z direction, and therefore remain we will still have some surface charge, and this is called transverse piezoelectric effect, where the strain is applied perpendicular to the Pauling direction, which is the z direction. The crystal was pulled along the z direction, and when the strain is applied perpendicular to the Pauling direction, it is called transverse piezoelectric effect. And there is the last one is called shear piezoelectric effect. In the shear piezoelectric effect, this is again applied in the z direction, which leads to change of the x component of the dipole moment. It is turned the angle, and corresponding charge also changed, and this is the shear strain is applied in the z direction, and that is called shear piezoelectric effect. And so, what we see here in the crystals, if the Pauling is done in z direction, if we apply the strain along the Pauling direction, then we say it is a longitudinal piezoelectric effect. If strain is applied perpendicular to the Pauling direction, it is called transverse piezoelectric effect, and while transverse piezoelectric effect, if it is done shear method, it is called shear piezoelectric effect. So, here by applying the mechanical stress, we see how the surface charge changed, and therefore, electric voltage, electric potential is generated. We can do opposite way also. We can apply the potential and see how the material deformation occurs, that means length and width changes of the in the material, that is what the inverse piezoelectric effect or that or indirect piezoelectric effect, that is what used in our STM as an actuator. So, now I have told in previous while describing the previous slides that Pauling is done along the z direction for this PZT crystal. So, what is Pauling? So, it is like and Pauling is done with PZT to impact the piezoelectric effect inside the material. So, like in a macroscopic crystal structure which composed of several unit cell, the dipoles are found to be oriented randomly, as you see in the A. Dipoles are found to be oriented randomly, and when we apply the mechanical stress, each dipole will rotate from its original position to a direction. Each dipole will orient from its original position to a direction that minimizes the overall electrical and mechanical energy stored in the dipole. So, in this way they will reorient. However, that reorientation is again not enough to produce the good dipole moment, because initially it was randomly oriented. In this case there was randomly oriented. So, net polarization was almost 0 or negligible. So, we have to create states where most of the dipole moments are aligned along the direction or more or less in the same direction of the applied field. So, this, in order to create an alignment of the electric dipole, one can, in order to create an alignment of the electric dipole in a particular direction, is called pulling. This is called pulling, and the direction along which dipole aligns is called the pulling direction, and the pulling is done by applying a very high electric field to the material. By applying a very high electric field to a material would orient all the dipoles in the direction of the field, and when it is done before pulling this was, and it is during the pulling high electric field is applied and they orient in the direction of the field, and this is what the material is pulled. And once we remove the electric field, they will not reorient back to the original position. They will almost remain in the almost similar orientation what is done during the pulling, and they will not come back to the original position as a result of pinning effect produced by the microscopic defects. Due to the pinning effect, they will not reorient to their original position, but remain aligned in the crystal, and this material is called pulled. This is pulled, let us say, in along the z direction. So, by pulling we can orient the dipoles in a crystal, thereby impacting the piezoelectric effect as that done with piezoelectric, that means as done with lead zirconia titanate. So, this is what done, and if this is what the pulling, whether we can depole or we can do reverse. Yes, if we apply again electric field in opposite polarity, opposite direction, then we can again reorient back them to randomly. By applying the field in opposite direction, material can be depoled. There is another way material can be depoled if it is heated to a temperature above the Curie temperature. If we heat this material, the pulled material, to above the Curie temperature, then this dipole reorientation will occur. They will again orient randomly and produce no net dipole moment inside the crystals. So, there are two ways it can be dipoled. One can be again applying the field in opposite direction or heating it above the Curie temperature. So, now how the extension of piezoelectric actuator occurs in an STM. So, as we see that piezoelectric scanner is used, which allows the tip to scan over the specimen. So, it has to extend its length x direction, y direction, z direction, every direction, then only it can able to scan. So, how the extension occurs? So, let us say it is a rectangular piezo plate with which is pulled in the z direction. So, now in these cases the external applied field, if we apply the voltage along the z direction, the applied electric field would be, the external electric field will be external applied field would be we can write E is equal to del V by Z, del V by Z. Here as field applied in the Z direction or voltage applied Z direction, we can write 3. So, 1, 2, 3 are normally labeled for the direction of x, y, z, x, y, z. So, here the external applied field is equal to del V by Z. So, now as a result of applied field, a strain will be generated inside the material along the Z direction, and also via the transverse contraction of the material, a transverse strain also will be generated in the x direction. And the piezo plate, if this piezo plate has a thickness of Z, piezo plate has a thickness of Z, it will be strain of del Z, that means the thickness changes by a value called del Z. So, we can write that the strain developed let us say we can write strain strain S is equal to del Z by Z. So, in the Z direction, as we are saying that 3, I write here 3, S3 is equal to this is the strain, this is the longitudinal direction. Longitudinal strain. So, at the same time, the transverse strain can be written as S1 is equal to del x by x, So, now the mechanical strain developed in this piezoelectric material, this mechanical strain developed in the piezoelectric material is proportional to the electric field, with piezoelectric coefficient as a proportionality constant. So, this strain is proportional to the electric field with piezoelectric coefficient as a proportionality constant. So, piezoelectric coefficient is defined as the ratio of the strain component in a particular directions to the applied field, and thus we can write the piezoelectric coefficient for, let us say we can write piezoelectric coefficient as D is equal to strain component, let us say is the S3 divided by E3. Here as both are 3, I write D superscript 3 double 3, or I can write here it is a piezoelectric coefficient, and this is done in Z direction, that is a longitudinal piezoelectric coefficient. Similarly, we can write in the transverse direction as D31 is equal to S1 divided by E3. This is will be transverse piezoelectric effect, transverse piezo coefficient. So, piezoelectric coefficient is this coefficient is a material constant which depends on the direction along which the electric field is applied and the direction along which the strain is developed or considered. So, here one important thing is that piezoelectric coefficient strain is here dimensionless, strain has no dimensionless. So, piezoelectric coefficient unit will be electric field volt per meter by volt. This piezoelectric coefficient unit will be our meter per volt, or in the STM it will be in the STM the piezoelectric coefficient will be, this will be angstrom per volt. The change of the length will be in the meter, not meter, in the angstrom level, and this volt will be, voltage will be in the millivolt region. So, it will be presented as the unit of angstrom per volt for piezoelectric coefficient. While this piezoelectric coefficient is a material constant that depends on the electric field and the strain. On the other hand, there is another term called piezo constant. Piezo constant is assigned to a specific actuator material, where piezo constant depend on the dimension of the piezo element and the electric field applied along a specified direction and the strain developed in a specified direction. So, the piezo constant is the ratio between amount of the motion in certain direction and the voltage applied between that electrode. So, now we can write piezo constant if the voltage applied in the z direction, the piezo constant that means that if we apply the voltage in the z direction, amount of motion is now del z. If the voltage is applied at del V, this is del z by del V is a piezo constant. This is amount of motion in the z direction and the voltage applied. So, this del z by del V can be written as del z by z, then z by del V. It can be written as like this, which is nothing but, which is del z by z is S3 and del V by z is z by del V divided by E3. It is divided by S3. So, the piezo constant along the z direction del z by del V is S3 by E3. As we see here, here the piezo constant does not, in this case piezo constant does not depends on the dimension of the piezo plate or piezo material. So, the motion of the piezo constant in the z direction means the longitude direction, is not depending upon the thickness of the plate or any other dimension of the plate. This means that piezo coefficient of the plate cannot be varied by tuning the dimension of the material. This cannot be done. So, but if we want to extend the only way to extend or enhance the length extension of the piezo element is to stack several piezo plates together, so that we can have a make these piezo plates to extend a more length, or to a greater length. This is about del z by del V is about the piezo constant in the longitudinal direction. On the other hand, if we consider about by transverse, because there is also a change in the plate change in the extension in the x direction, also changes. So, piezo constant in the transverse direction del x by del V, that is transverse direction, del x by del V can be written as del x by x into x divided by del V by z into z. This can be written as like that. Then del x by x is equal to S1, del V by z is equal to E3 into x by z. And S1 by E3 is equal to D31 into x by z. What we see here, for del x by del v, which is again a piezo constant in the transverse direction, that depends on the dimension of the piezo plate. Like if x is more, then piezo constant will be more in the transverse direction. If z is small, thickness is small, piezo constant will be more. So, in order to increase the piezo constant in the transverse direction, we can make a longer and thinner piezo plate. However, if we use a very thin and long piezo plate, then its resonance frequency will be less. Moreover, one problem is that it will have a low resonance frequency, and which is disadvantageous for scanning probe microscopy. And second point is that if we use very thin or Z is small thin plate, then the potential may reach to its highest level, after which we cannot apply more potential. So, the electric field will reach to its limit. So, up to a level x can be increased or z can be decreased, above which it will again create problem. Therefore, piezo plate is not used in the STM, rather a piezo tube is used. Piezo tube is nothing but a rolled up, we can roll up a plate or thin plate to make a tube, and we will see that actually in STM, instead of using piezo plate, we use a piezoelectric tube. That is what we will discuss in the next class, how just for the sake of understanding about the piezoelectric effect and the transverse piezoelectric effect, longitudinal piezoelectric effect, piezo constant, piezo coefficient, etc. I have taken a simpler example of a piezo plate, but in STM we use piezoelectric tube, and how a piezoelectric tube function in a STM we will discuss. In addition to that, we have so far discussed piezoelectric coefficient, piezo constant in the longitudinal and transverse direction. We have another is shear. We have shear. Piezoelectric plate also piezoelectric coefficient can be seen through shear strain. A piezoelectric plate is shown here, which is poled again in the z direction, while electric field voltage is applied in the s direction. This leads to a shear strain along the z direction, and now we are writing here shear strain as del z by x. And now in these cases piezo constant, in these cases shear strain effect, piezo constant will be del z by del v, will be by convection is written as 1/5. Before we had three term 1, 2, 3 for x, y, z. One is for here x direction, piezo constant is going in the x direction, and 5 is for this shear effect. This is by convention we use piezo constant for shear effect, for a shear strain effect d1/5. This is about the shear strain effect, and in our next lecture we will discuss about how a piezoelectric tube works, that is what used in the scanning tunneling microscope. Thank you.